Welcome back, everyone. This is the final lecture in Chapter 32 and the final lecture for the E&M AP course. In today's lecture, we're going to look at a couple things. We're going to look at the energy that is stored in an inductor. We're going to look at how we actually would calculate the inductance of an inductor, specifically of a solenoid. And we're also going to look at some CL circuits or some LC circuits. Okay, so let's get started. First, looking at the energy that is in an inductor, what I first want to do is go back to Kirchhoff's law that we looked at in the previous lecture when we were looking at LR circuits. And again, specifically, we're looking at this situation here where you have a circuit with a switch that's connected to a resistor, an inductor, and an EMF source. So if I were to write out Kirchhoff's law for the situation, epsilon is going to be equal to IR plus L di dt. All right, so this is the EMF from our battery, the voltage drop across the resistor, and the induced EMF from the inductor. Okay, so we want to start looking at energy, and we know that energy is closely connected to power. So if I take this equation and I multiply it through by I, the result that we get looks something like this. I epsilon, which is equal to I squared R plus L I di dt. Now, if I take a look at this equation closely, I can see that these are actually expressions of power, right? This is our equation for the power that is being provided by the voltage source, or the EMF source, IV, right? P is equal to IV, so that's where this first term comes from. So we'll just call this the power from the battery, right, being supplied to the circuit. The second term, I squared R, well, that's the power dissipated through the resistor, of course. So power dissipated in the resistor. Therefore, this last term must represent the power that is going through the inductor. Right? This must be some numerical value of power because all the other terms in the equation are power. Okay. So specifically, this is going to be the rate at which energy is stored in the inductor. Right, we know that energy is stored in the inductor because it's very similar to kind of what we looked at with capacitors, where you had the energy stored in the electric field that was between the two plates of the capacitor. Well, the magnetic field then must also store energy as the current is running through it, because as the current runs through it, it creates this magnetic field, right? Energy is certainly being stored there. Okay, so we have an idea of at least what this term, right? What the term for the power, at least, for this inductor is going to be. So we know power is connected to energy, so let's go ahead and do that. Let's make that connection. So the first thing I'd like to do here is define UB as the potential energy stored in the inductor. And again, we're using U sub B to indicate that it's, the potential energy from the magnetic field that the inductor has. Okay. Well, we know that power is the rate of change of energy. So the power in the inductor must equal the rate of change of the energy in the inductor. And that's all going to be equal to what we found out in the previous equation, which was Li di dt. Okay. So I'm going to take the right two parts of this equation, and you can see some things are going to simplify. So the dt's are going to cancel, and the result that we are left with is dUB is equal to Li di. Okay. Well, ultimately, we want to know what the total amount of energy is that is stored in the inductor at steady state. So we'll just take the integral of both sides. The integral of this side, we'll do the integral of that side. So the total energy stored is going to be equal to 1/2 Li squared. Right? That just comes directly from the integration of that equation. L is a constant, that doesn't change. We do the integral of the current, right, which could change. But again, this is really just giving us the energy at some steady state for the inductor. So there you go. All right, so let's jump over to the next page. We're going to look at the inductance of an inductor. So in previous lectures, I've mentioned that the amount of inductance in an inductor has to do with the physical dimensions of that inductor, right? We talked, again, very similar to what we talked about with the capacitor, right? The plate separation, the area of the plates, right? All those things impacted the actual capacitance of the capacitor. Well, same thing here with the inductor, the physical dimensions, how many loops there are of the inductor, which is generally modeled as a solenoid, affects the amount of inductance that it could have. So, let's take a look at a couple things. First of all, the inductance, which is L, right? It's a measurement of the inductance of an inductor, is equal to the amount of loops, N, multiplied by the flux, the magnetic flux, divided by the current, right? This comes from one of our previous equations. It's just showing us that there's a relationship between the inductance, the flux, and the current. Let's also remember that the magnetic field of a solenoid, so B sub S, was mu n times the current. Sorry, mu naught n times the current. Now, let's define what both of these n's are because they are really different things. The capital N is essentially the number of turns, and lowercase n is the number of turns per unit length. Right, so they're slightly different than each other. Let's go and just write them in the same form because they are related. So this is really mu naught capital N over L times the current. Okay. Now, we also know that the flux is the magnetic field multiplied by the area, so another way to write this first equation is going to be N times the magnetic field multiplied by the area divided by the current. Okay, so I'm going to take my expression for the magnetic field and put it into this expression, and you're going to see that a lot of things end up canceling, so these two things come together, and what we end up with is the inductance is equal to mu naught times the number of turns squared divided by the length multiplied by the area. Okay, so again, we told you that the inductance is a property of the actual object, the physical dimensions of the object, of the solenoid. So how many turns does the solenoid have? How long is the solenoid? And what is the cross-sectional area of the solenoid? Okay, that is all that the inductance depends upon. All right, and for the last slide, let's talk a little bit about LC circuits. All right, so LC circuit, of course, is going to be an inductor-capacitor circuit, and the E&M course doesn't really get too far into this, just have a basic understanding of what's going to happen here. So let's set up the situation. At time t is equal to 0, let's say maybe there's a switch or something in this where you have just closed the switch, but before that you had to have charged the capacitor, right? Ultimately there would have to have been something here to indicate that there was energy already in this circuit, right? It's not just going to magically appear. So the energy is already here that's stored in this charged capacitor, and you put it into a circuit now with an inductor. So how does this behave? Well, I think it's obvious to see that, because this is now a closed loop, you're going to see the positive charge from this end travel around and end up over here, right? Of course, we know what's actually happening is the negative charge is traveling in the opposite direction, but the direction of our current is always the direction of the positive charge, so you have a current that's going in that direction. Now, this current is going to change because you're essentially going to get up to a point where you get to a maximum current, right? It's going to take some time. The inductor is impeding that flow, right, as we expect it to do. So the current starts off at 0, but then sort of builds up to a maximum amount of current. When it gets to the maximum amount of current, all of the energy is now essentially in the inductor because you've taken the energy from the electric field that was stored inside the capacitor, and you have caused this current, caused that energy to now move so that at max current, all that energy is now in the inductor. Then, of course, you end up with continual current in this direction, and you're going to end up with some excess positive charge ending up on this plate. Because you have excess positive charge on one plate, you're going to end up with excess negative charge on the other, and you eventually get to the point where all the energy gets put back onto the capacitor. The current then goes to 0, and the reverse happens. Right now you have a whole bunch of positive down here. It wants to get to the negative, so it travels the other way, right, all the way up to maximum current, where all of the energy is stored here in the inductor, and then the kind of process repeats. So, if we take a look at the two graphs at the bottom, you can kind of see that happening here. You have the current, which is our blue line, and you have the charge, which is our orange line. And again, this is the charge on the capacitor plate. So, when current's at its max, notice how the charge on the plate is 0, right? So that's going to mean at this moment, all the energy is in the inductor. None of the energy is in the capacitor. Then the reverse happens, right? You're going to eventually go back to a current of 0. You now have all of the charge on the other plate of the capacitor, which you see happening here. This obviously looks like a sine curve or a cosine curve. These are essentially an oscillating situation, right? It's going to oscillate back and forth, which is very interesting because it's not oscillating because there's an EMF source. It's oscillating because of the conservation of energy, right? These two energies continually just go back and forth with each other. We have seen this before with a spring oscillator, right? Just as a quick reminder, you have a spring oscillator attached to a spring. There's a block here. It's going across a surface. At equilibrium, it has all kinetic energy. Over here, when I stretch it out to the amplitude, it has all elastic potential energy, right? Same thing when it gets over here. It has all elastic potential energy. So, sorry, that's not negative. It's always positive. So, we've seen this form before. We've seen oscillators before. We don't need to know how to dive into those equations too much here, but just understand that the energy is conserved in this process. So if I were to write a conservation of energy equation, I guess I may be looking at the situation where all the energy is in the capacitor, and then all the energy is in the inductor at a later period of time. You could simply say that they are equal to each other. So we'll just say the energy at A is equal to the energy at B, right? Our general conservation of energy equation. So we start off with all of it being in the capacitor. So it's going to be 1/2 Q squared over C, or 1/2 the charge squared divided by the capacitance. And then at a later time, it's going to be all in the inductor. So that's just going to be 1/2 Li squared. Okay. So this would be, a conservation of energy equation that you could use. And the last thing I'll just mention here is if you wanted to know what the energy was at any given time or any particular point, not necessarily the time, but maybe at any particular point, the total energy is simply going to be the addition of these two things, right? It's going to be 1/2 Q over C squared plus 1/2 L I squared. Where there's a couple of variables here, right? The Q is going to be a variable, the I is going to be a variable as well. So just kind of keep that in mind. Okay, well that's it for this lecture. That's it for the E&M course. You've made it through. Congratulations, and we'll see you next time.